Hi, my name is Bernard Santos. I'm going to be doing a presentation for physics um, to show you the concept of series circuit, parallel circuit, as well as the relationship for the formula V is equal to IR, or the voltage is equal to the product of current and resistance. So to start with our demonstration, we have our materials. We have our 9-volt battery, our LEDs over here, and our breadboard. The breadboard is basically a board where we could put in components without soldering it, and it's for this row it's connected horizontally, and for the other rows it's connected horizontally. So let's start with the parallel circuit first, which is this row of LEDs on the very top of the breadboard. And to show you the schematic diagram, this is how it would look like. So basically, those LEDs are connected in parallel. We have our 9-volt battery here, and then our 3 LEDs, where the current would run from the negative to the positive. So let's do that in the experiment. Okay, so as you can see, all of the lights or the LEDs are on. Now for the series circuit. The series circuit is the one below here, and it's basically connected, as the name implies, it's in series connection, and the schematic diagram would look like this one. So we have our 9-volt power supply and our 4 LEDs, and of course when we turn on the power or attach the battery, the current will run from the negative terminal around the diodes, or the light emitting diodes, and back to the 9-volt power supply. So let's see if it works. And there you have it, a series circuit. Now, as an analogy, you could think of the electricity as water flowing from the main source towards the load or to the faucet. This would serve as a faucet. And for the parallel circuit, the water would basically flow through this pipe and then be distributed towards the outlet and back into the main source. With series, it would look like this. If electricity would be like water, it would run from this part and would run through these faucets, and the current would serve as a pressure, the water pressure. Now, why are we demonstrating the series and parallel circuits? So just to give you an idea what the advantages of having a parallel circuit. Basically, for the parallel circuit, one advantage is that if one bulb goes out, the other two would still light up, because the current will run through the other two bulbs even if the connection gets disconnected. So that's one of the advantages of having a parallel circuit. So let's see if that would work. Let's just attach the power. So as you can see, all the three bulbs or LEDs are lit, and let's see if we remove one, it would still have those two lighted. See? So as you can see, even if I remove one of the LEDs, the rest would remain lit because it's not affected, as we mentioned before, because of the distribution of the current in this one. Another advantage of a parallel circuit is that the cell would last longer because it's distributed equally over the LEDs, and each bulb would receive the same voltage that is supplied by the electric source. The disadvantage of a parallel circuit, however, is that the voltage does not increase or decrease if cells of the same type are connected in parallel. And another disadvantage is the electric current in the circuit is the same even though more cells are connected in parallel. Now let's go with the series circuit. Now for the series circuit, the disadvantage of this is that if one of the bulbs or the LED breaks, the rest won't light up. So basically the current in all parts of the circuit is the same. This causes the bulbs to light up with the same brightness. And another advantage of it is the current in the circuit increases if more cells are connected. And lastly, all circuit components are controlled by one switch. Basically, again, like what I've said, if one of the LED gets broken or disconnected, then the rest won't light up. And that's one of the disadvantages, because there is only one path for the flow of the electric current, and if a bulb or lamp is burnt, let's say this one, the fourth one, then the other bulbs will not light up. Another disadvantage is cells in series do not last long because it's basically powering up the 4 LEDs or the load in sequential orientation. And lastly, one of the disadvantages is that if more bulbs are added, the resistance in the circuit increases, causing the electric current that flows to decrease. Because let's say these are if we're going to go back to our previous analogy of water, if this would be faucets, if we add more faucets and turn it on all at the same time, the water flow or the pressure would go down because more faucets are going to be open or more people will be using the water. So it goes the same for the series circuit with the same principle of the water flowing through a pipe. So let's look at see that in our demo. Let's attach this one. Okay, so as you can see, all the LEDs are lit up. However, if we remove one of the LEDs, the rest won't light up because the circuit would be broken as we've shown here. So let's say if we remove one, the rest would turn off because the circuit is broken. So same with here. Alright, it would turn off. Same with here. So that is how a series circuit works. Okay, so let's continue with our discussion. So right now, we're going to proceed with the parallel and series circuit demo. And what we have here, these three resistors are connected in parallel configuration, and this one is connected in series configuration, and each resistor is rated at 680 ohms resistance. So again, our power supply or our cell is rated at 9 volts. So if we're going to be connecting our battery here in the parallel circuit, we should be getting a voltage drop near 9 volts, considering that each resistor would provide resistance. So going back to our formula, where V total is equal to V1 is equal to V2 equal to V3, and I total is equal to I1 plus I2 plus I3, and resistance total is 1 over R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So let's see if we could prove this equation or the formula that we have, or the value that we have, by connecting the battery. So let's connect this battery to our parallel circuit. Okay, and then let's test. We should be getting a reading that's almost or close to 9 volts for each of the resistors that we have. So for the first one, we have 8.7 volts. Second one, we also have 8.69 or close to 7 volts. The last one is 8.6. Okay. Here, so it's 8.6, where we seem to be losing power, so that's why the readout is fluctuating a little bit or decreasing a little bit. So we have 8.6 for the first resistor, 8.6 for the second, and 8.64 for the last. So that's for the parallel circuit. So now we know that the value for this one is correct. So from that, we could even compute for the value of the current, which is what we have here. So for VT, we have the IT, or the V total, voltage total is equal to the current total multiplied by the total resistance. We already know that we have a 9 volt battery source, and each resistance is at 680 ohm. Here, 680 ohm. So by following the formula, we will be getting the total resistance of the circuit or the parallel circuit, which is at 226.67 ohms, and substituting that value to get the current, we have V total is equal to I total times R total. We have 9 volts is equal to I total times 226.67 ohms. So 9 divided by 226.67, we get the current. And again, we've already proven that from the equation or the value, we have V total is equal to V1 is equal to V2 is equal to V3. So therefore, we have the voltage drop of 9 volts or 8 point, in this case it's 8.6 throughout. So there you have it. So V total is equal to 9 volts, equal to 9 volts, is equal to 9 volts, and V3 is equal to 9 volts. But in this experiment, since we use the value of, we use the measurement, we get 8.6 all throughout the equation. So that's 8.64, which is, if we're going to round it up, it would give us 9 volts total. That's it for the parallel. Alright, so now let's go with the series circuit. So we have here a series circuit configuration, and based on the formula that we have for the series circuit, for us to get the total voltage, we have to add V1, V2, V3, and so on and so forth. If we have more than 3 resistance or load that we have, because we have to add this 1, 2, 3, we have to add those things, or those resistors, the voltage drop on each resistors. So to get the current for a series circuit, the current is equal throughout the circuit, since they're already in series. So the current running through this circuit, or through this circuit, would be the same throughout each load or resistance. And for the total resistance, we have to get the summation of R1, R2, and R3. So we already have a given of 9 volts for this battery, or from what we measured before, which is 8.6, or again approximately 9, and the resistance of each resistor, which is 680 ohms. This one, 1, 2, 3. R1 is equal to R2 and R3 in terms of value, since we only have one pack of 680 ohm resistors. So again, what we're going to compute for are the voltage drops for each resistors, and see if it would satisfy this equation. So we already have a computation for that, and here we have it. So for the computation, or the solution for series circuit, we have the V total is equal to I total times R total. We have the voltage, or the voltage rating for our battery, which is 9 volts, and the R total is the summation of R1 plus R2 plus R3. Substitute, getting the value, which is 680 ohms. 680 ohms plus 680 ohms, we get 240 ohms. So that means this one, first resistor 1, resistor 2, resistor 3 has a total resistance in series circuit of 240 ohms. Substituting the value, we have V total is equal to I total times R total. Again, the value of our V total is 9 volts, is equal to I total. Substituting the value of the R total, which is 2040 ohms, we get the I total of 0.0044 amperes. And in a series circuit, I total is equal to I1 is equal to I2 is equal to I3. So substituting that value, we have V1 to get the voltage drop. Substituting each value for V1 is equal to I1 times R1. So that is 0.0044 times 680, which gives us 2.999 or 2.999 volts. And rounding that off, we get 3 volts. So that means for each resistor, we should be getting a reading close to 3 volts, and adding that up, we should get 9 volts to satisfy this equation. So let's connect the battery and see what we get on the reading. So we have our battery here, and we have our meter. So let's see the reading. Okay, so we have, for the first resistor, we have a voltage drop of 3 volts. Second resistor, we have a voltage drop of 3, and the last, we have voltage drop of 3. So the total of this should provide us 9 volts. Again, each resistor provides a voltage drop of 3 volts. That's for R1, and for R2, 3 volts as well. For R3, it's 3 volts. And if we get the total of it, we get 9 volts, which again satisfy the equation that we have right here. So we get the 9 volts. And there you have it. The series parallel demonstration for physics.